Hi, I'm Ann-Sophie Allgaier. Together with Abby Turner and Artur Dabrowski in the Autumn Lab, I've been working on scalable, higher-order graph attention networks for money laundering detection. Much of the data found in real-world applications is inherently graph-structured. For example, social networks, traffic networks, or financial networks. We focus on the use case of money laundering detection. Financial networks with some transactions, often modeled as edges, may be used to cover up the original illicit source of the money routed. Launderers in these networks consider proceedings to deliberately convoluted flows. This means that the signal often lies not in individual transactions, but in the joint interactions at subgraph level and in the topology of the graph. This is just one example of higher-order signal being important for graph-based tasks. However, the existing state-of-the-art approaches, namely graph neural networks, perform pairwise message passing, meaning that they update a node's feature vector by aggregating the individual feature vectors of the nodes in the direct neighborhood. Pairwise message passing captures higher order dependencies only indirectly through that, often leading to oversquashing, meaning that information gathered across many layers has to be condensed back down in a fixed dimensional embedding, causing information loss. Existing high order methods are mostly theoretical work, scaling polynomially, and are thus impractical to apply to large-scale datasets. Consequently, this project is focused on extending graph neural networks to the higher order setting at tractable compute and memory cost. The approach is focused on enriching a node with the information about the joint interaction of nodes found in its neighborhood. For that, 3 steps are applied. First, sampling to keep the computational time tractable. From the neighborhood, a budgeted admissibility filtered candidate set is selected. Only from these candidates are k tuples constructed. These tuples are lifted to a hypergraph to attend over by computing a permutation invariant pool, generating one feature vector for each tuple. To enrich the node with the information about its higher order neighborhood, attention is then performed over the embeddings of the admissible tuples, separately at each tuple order, from pairwise order up to the maximum tuple order k, and the representation across tuple orders are then used to update the node's embedding. The approach is evaluated on the synthetic anti-money laundering transaction network of Altman et al. 2023, namely the small hi version, which is a directed multigraph with 0.1% illicit edges. The task is binary edge classification, so to label each transaction as licit or illicit. 2 experiments are reported, and for each, the test AOPRC and F1 score, due to the fact that the data is extremely imbalanced, these are the reliable metrics, and for them the mean and standard deviation across 5 seeds. One experiment directly compares the influence of higher order attention by running the method once with just a pairwise arm and once with the pairwise arm and in addition the free order arm, so triples, at the same feature encoding, same backbone, and the same sampling. This is shown in the graph on the right, and it directly illustrates the marginal benefit that can be gained from adding higher order attention, getting an improvement in AOPRC score by a percentage of delta 11.7%. This is a small marginal improvement, but it shows a positive signal of the effect of including higher order attention. The second experiment compares the free order method against the standard baselines in this field, a multi-GIN graph isomorphism network and a multi-GAT graph attention network. The multi refers to a series of additions that are added to the GNNs to make them adaptable to this specific dataset. They were proposed in provably powerful networks for directed multigraphs by Agresti et al. To keep it short, the additions are 1 reverse message passing, meaning tuples attend not only over outgoing nodes but also incoming ones, and ports to enable the nodes to better understand where a transaction comes from. Both of these additions are also used in this evaluation of the higher order approach to fit it to the dataset. The baselines furthermore use a third addition, ego IDs. These are specialized encodings added to the node features to enable them to understand if they're part of a circle. Adding to that, the multi-gin and multi-gap baseline further has access to a larger neighborhood, since the higher order approach has to rely on a more sampled neighborhood. Nevertheless, the results showed that the higher order approach is able to match or even very closely outperform the baselines. This shows that higher order structure carries laundering signal for this dataset and is a positive signal for further applications. Nevertheless, the cost has to be mentioned, with the higher order approach needing 2.4 times as much parameters and 6.7 times as much time per epoch. But this is something that can be directly targeted in future applications, which are focused on further working on the sampling method, eventually going to a task-driven sampling that is able to directly learn which candidates to select end to end. Also, cheaper attention mechanisms that are applied in graph learning can be considered to directly target the overhead. The main takeaway is that, first of all, many graphs contain significant higher order signal that Paris message passing captures only indirectly, and that higher order methods, specifically the proposed methods, already shows promising results directly incorporating that higher order intention with a small marginal improvement in performance. Thank you.